In this video, we'll discuss normal distribution, which is a very commonly used continuous distribution. Normal distributions depend on two parameters, mu and sigma squared. So let mu and sigma squared be two constants. The mu can be positive or negative or zero, while sigma squared is always strictly positive. So these are two constants. A random variable x has a normal distribution with parameters mu and sigma squared, or in short, mathematically we can write x follows the normal distribution with parameters mu and sigma squared if the following is its density function, if the probability density function of x looks like the following formula. So the density function is 1 over square root 2 pi times sigma times e to the power minus x minus mu squared divided by sigma squared. So in this density function, there are two mathematical constants. So the mathematical constant pi is familiar to everybody. So that's the number that's approximately 3.14. Then there is another mathematical constant, e. This mathematical constant we discussed in the video about Poisson distribution a week before. So that is, E is the continuous compound constant. It's related to the multiplier when you continuously compound interest in your bank account. And E is approximately 2.71828. So this is the probability density function of a normal distribution with parameters mu and sigma squared. So this e to the power something is sometimes also written as, may also be written as exp lambda, and it's read as exponential lambda. Exponential lambda is e to the power lambda. So in this notation, the density of the normal distribution may also be written as 1 over square root 2 pi times sigma times exponential minus x minus mu squared divided by sigma squared. So these are just two ways of writing the same thing. So that's the normal distribution. The normal density looks like a bell. It's the bell-shaped density function. When you draw the density function on the graph, they look like a bell. And regarding how fat or how thin, or how high and how low, or where the center of the bell is, those are dependent on the parameters mu and sigma squared. So in this graph, we have 4 density functions pictured. So the red curve is the probability density function for the normal distribution with parameters 0 and 1, and that is this density function. And for normal distribution with parameters 0 and a smaller sigma squared, the density function is more concentrated around 0. It's taller and thinner. And a normal distribution with the same mu but a bigger sigma squared is more spread out. So it's fatter and flatter than the normal distribution with parameters 0 and 1. Well, changing mu will change the center of the distribution, will change the center of the probability density function. So when you change mu from 0 to -2, you can see the probability density function, the center of the probability density function moves to -2 from 0. So from 0 to -2. So what are these particular parameters? How are they related to the traits of the distribution? Well, you can calculate using the definition of expectation that expected value of x is in fact equal to mu, and the variance of x is equal to sigma squared if x is normally distributed with parameters mu and sigma squared. Deriving these equations, deriving the first equation about the expectation is not very hard. It's just the usual integration of the exponential function. And deriving the variance, you use the formula for the integration of exponential function as well as integral by part. In this course, we do not require such mathematical details, so I will not go over the derivation. So just, but it's very easy to remember that mu, the first parameter mu is the mean of the normal distribution, is the expectation of the normal distribution. And the second parameter is the variance of the normal distribution. Now, we talked about shifting and scaling uniform random variables. We can also shift and scale normal random variables. So we claim that, so we already know what shifting and scaling means. And now we can just claim that if x is normally distributed with parameters mu and sigma squared, with mean mu and variance sigma squared, then ax plus b is also normally distributed, but with mean that's given by a mu plus b, and variance that's given by a squared sigma squared. So the proof of this is actually quite accessible. So proof, now we suppose that A is positive. You can go through an analogous process to show the case where A is negative. But now let's just say A is positive. Then we call this random variable, let's say this is y. Then the CDF of y is given by probability that y less than or equal to little y. And that's given by probability ax plus b less than or equal to little y. And because A is positive, the inequality in here is equivalent to the inequality about x. So x less than or equal to y minus b divided by A, which is, by definition of CDF, is the CDF of x evaluated at y minus b divided by A. Now, in order to get the PDF, we simply take the derivative of the CDF. And that derivative is applied on this expression of the CDF and this is a compound function of y, so we can use the chain rule for taking the derivative. So using the chain rule, we find this derivative equals density of x, y minus b divided by a, times the derivative of y minus b divided by a with respect to y, which is 1 over a. So that, in fact, is square root 2 pi times sigma times a. So a sigma exponential. Actually, let me move here because I want more space. Exponential minus y minus b over a minus mu, because x has expectation mu, squared divided by sigma squared. If you simplify this equation, you find that this is in fact a squared sigma squared y minus b minus a mu squared. And this is exactly the probability density function for a normal random variable with mean given by b plus a mu or a mu plus b, and with variance given by a squared sigma squared. So it's this normal distribution. So that the claim is proved. So when you shift and scale a normal random variable, you obtain another normal random variable. And we can use this result to turn any normal distribution into a standard normal distribution. So what is the standard normal distribution? Standard normal distribution is the normal distribution with parameters 0, 1, with mean 0 and variance 1. We can generate any arbitrary normal distribution from a standard normal distribution by shifting and scaling, and vice versa. So we can see that. So suppose that x is normal mu sigma squared, then we can shift and scale x and define a new random variable y, and y is x minus mu. So we shift x to the left by mu units and then scale by 1 over sigma. Then this y random variable follows standard normal distribution. Why so? Because this is a shift and scale, shifting and scaling. So y is obtained by shifting and scaling x, and we know shifting and scaling x will still give you a normal random variable, and with the parameter given by this. So we know this is a normal random variable, and what is the expectation of that? Expectation of y is expectation of x minus mu divided by sigma. Well, that is expected value of x minus mu divided by sigma. Expected value of x equals mu. Therefore, this is 0. And variance of y is the variance of sigma 1 over sigma x minus mu over sigma. And that is 1 over sigma squared variance of x, which is sigma squared over sigma squared, which is 1. So therefore, y is a normal random variable with mean mu and variance 1. So that's standard normal. That's how you can turn a general normal distribution into a standard normal distribution. And that is very useful because suppose we want to calculate the probability that x is between some interval. This is actually not very easy to do because the CDF of normal distribution, of any normal distribution, doesn't have a simple closed form. So you cannot use your pen and paper to figure out the probability of x belonging to any interval. But we can, however, using this scaling and shifting to turn this probability into a probability about y, about this standard normal distribution. Probability that x belongs to A and B equals the probability that x minus mu belongs to A minus mu, B minus mu. And that equals probability that x minus mu divided by sigma belonging to A minus mu divided by sigma, B minus mu divided by sigma. So that is probability that a normal 0, 1, the standard normal random variable, belongs to A minus mu divided by sigma and B minus mu divided by sigma. So we only need to know how to calculate the interval probability for standard normal random variable. And that's enough for us to figure out easily the probability that a general normal random variable belongs to some interval. So next, we're gonna focus on how to figure out interval probability for a standard normal random variable. You will see that here, even here, I call this shifted and scaled random variable y, but the generic notation for standard normal random variable is in fact z. So we will use z a lot to denote a standard normal random variable. So typically use the symbol z to stand for a standard normal random variable. Well, whatever. So the symbol actually doesn't matter, but it's just a convention that people always often use z to stand for a standard normal random variable. So now let's talk about how to calculate standard normal probabilities on certain intervals. There is no general simple formula for calculating the probability that a standard normal random variable belongs to any interval, open interval, one-sided interval, or two-sided interval. In general, there is no simple formula to do that. But there are some basic properties that result from the shape of the probability density function that will be helpful for us to calculate those probabilities. Two basic properties that are very useful are a result of the symmetry of the probability density function. This picture shows you the probability density function of a standard normal random variable. Probability density function for standard normal distribution. As you can see, it's centered at 0 at the expectation. And the curve is perfectly symmetric on the two sides of 0 of the expectation. And this symmetry is useful and tells us these two basic properties regarding the standard normal distribution. The symmetry tells us that probability that the random variable is less than its expectation, less than the center, probability that x is less than 0, that should be 1/2, because that probability should be the same as the probability that x is greater than 0. And these two parts should add up to 1, and they should be equal, therefore each should be 1/2. Therefore, the symmetry tells us probability that z is less than or equal to 0 is 1/2, and that equals probability that z is greater than or equal to 1/2. And because this is a continuous distribution, so it does not matter whether we use less than or equal to or strict less than, or greater than or equal to or strictly greater than. So those do not make a difference because we are studying a continuous distribution. So that's one property resulting from the symmetry of the probability density function. The second property is the following. It also results from symmetry. Probability that z belonging to the interval AB is equal to probability that z belongs to the interval minus b to a, to minus a. That's simply because the interval a to b, let's say this is a, and this is b, and that is the probability, the area under the curve between this interval, that's the probability that z, so z is standard normal, z is in the interval AB. And the probability that z is in the interval minus b minus a is as follows. So a, the mirror point of a is minus a, and the mirror point of b is minus b. And the probability that x is in the interval minus b to minus a is this blue shaded area. The blue shaded area and the yellow shaded area are exactly symmetric to each other. They're mirror image of each other. So the probability are the same. So both of these properties follow from the symmetry of the probability density function. And also there are some approximate standard normal probabilities that you might see people using. So there is the probability that z is belonging to -1, 1. That is approximately 0.68, 27. That is approximately 2/3. So the probability that a standard normal random variable is less than or equal to 1 in absolute value is about 2/3. And the probability that z is between -2 and 2 is about 0.95, 45, I think. And that's approximately 19 divided by 20. And the probability that z is belonging to -3 to 3 is approximately 0.99. So I actually don't remember the fourth digit. So I'll just not write the fourth digit. So 22 is about 0.94 and 33 is about 0.99. And that's approximately 399 over 400. So you can find these numbers in the textbook as well. So these are just some special values, some approximation for some special values. And these are two properties coming from the symmetry of the probability density function. But what if you want to get the exact probability in some interval? You can use one of the standard normal distribution tables. And this is one of the tables. This table actually is the same table as the one in the textbook. In this table, the numbers given in the table are the probability for the standard normal random variable lying in some interval. But in what interval? In this interval, in the 0 to z interval, in that interval. So the numbers given in the table is the probability that the standard normal random variable is lying in the 0 to z interval, in this interval. Well, the z is given by the column titles, the row titles, and the column titles. So the row titles are the first digit are the z up to the first decimal point, while the column titles are the second decimal point of the z value. For example, if you want to know probability that z is in the interval 0, 1.21. Let's say you want the probability that z is in the interval 0 to 1.21. Then you're going to look for 1.2 in the row title. So 1.2 is here. And then you look for 1, the second decimal point, on the row, on the column titles, which is here. 0.01 is here. And the probability is given by the cell corresponding to this row and this column, this row and this column, which turns out to be this exact number, this number. It's 0.3869. So this is approximately 0.3869. So this is still approximately equal because the exact number for this probability probably has many digits, much more than 4 digits, but we can only fit 4 digits into the table. So that's approximate, still approximate, but close enough. So that's how you use such a standard normal table. And how do you calculate the probability that z is less than or equal to 1.21 then? You want to know the probability that z is less than or equal to 1.21. How do you calculate that number using this table? Well, that's easy. The probability that z is less than or equal to 1.21 is this event can be partitioned into 2 events. One is that z is less than 0, less than or equal to 0. And the other is z is between 0 and 1.21. So that is, therefore, that probability is the probability that z is less than or equal to 0 plus the probability that z is in 0 to 1.21. We know from symmetry that probability that z is less than or equal to 0 is 0.5. And we know from the table that this probability is 0.3869 approximately. Therefore, together that's 0.8869. And note that I couldn't remember the third and fourth digit of these probabilities. Let's try to figure that out using the table. So what is the probability that z is belonging to -3 and 3? Well, due to symmetry, that should be equal to 2 times probability z belonging to 0 to 3 interval. And the probability that z belonging to the 0 to 3 interval can be figured out from the table. You simply look for 3 in the row titles, which is here, and 0 in the column title. So it's this row and the first column, which give us 0.4987. 2 times 0.4987, and that's approximate, and that is equal to, we can multiply 0.49 to 87 by 2, and that should give us 4.799. So 0.9974. So I can put 0.9974 here. And similarly, you can figure out the third and the fourth digit for the other number that I couldn't remember from the table. Probability that z is between -2 and 2 should be 2 times probability that z belonging to 0 and 2. And let's look for this probability in the table. We simply look for the row indicated by 2. So we look for the row title 2 and use the number on the first column because there is no second digit. So we have 0.4772. And 2 times that is 4.459. So about 0.9544. That's our calculation from this table. It's how you use a standard normal distribution table. In fact, this is the table that our textbooks show us, but there are many other kinds of standard normal tables as well. So you may have seen tables like these. These are other kinds of standard normal tables. And the way to use them is the same. You look for the z number by checking the row titles and the column titles. The row titles give you the z value up to the first digit decimal point, and the column title gives you the second decimal point. And in the table, in the interior of the table, you have the probabilities. But what probability are these depend on the description of the table. And these tables are different from the one we just looked at. The numbers in these tables are in fact the lower tail probabilities, not the probability that z is in between the, not the probability that the standard normal random variable is in between z and 0. Not this, but the lower tail probabilities. Okay, so when you use the normal tables, you should be aware of what the normal table is, what the numbers shown in the table are. And those should be described at the beginning of the table. Because the textbook uses this table, we'll just focus on this particular normal table. Now we can do a simple example where we calculate normal probabilities. Suppose that you order pizza from a pizza delivery place, and you know from a large data set that the pizza delivery time, the time needed for your pizza to arrive, is a normally distributed random variable with expectation 30 and variance 5 squared. Then what is the probability that you get your pizza in 20 minutes? And what's the probability you get your pizza in 22 minutes? So what we want to calculate is probability that x is less than or equal to 20. Now, first we want to turn x into a standard normal random variable. We want to shift it and scale it so that it's a standard normal random variable. X less than or equal to 20 is equivalent to x minus its mean divided by its standard deviation less than or equal to 20 minus 30 divided by standard deviation. And that, from the previous discussion, we know that is standard normal random variable. We can denote that by z. And this number, in this case, equals -2. So therefore, that equals the probability of z, a standard normal random variable, less than or equal to -2. The probability that z is less than or equal to -2, how do you find that distribution? That distribution can be found by first use the symmetry. Probability that z is less than or equal to -2 is probability that z is belonging to -infinity to -2. And that equals probability that z belonging to the reverse image of that interval, which is 2 to infinity, and which equals probability that z greater than or equal to 0 minus probability z belonging to 0 to 2. And probability that z is greater than or equal to 0 is 1/2. And probability that z is in the interval 0 to 2 can be figured out from the table. Actually, it's one of the special probability that z belonging to the interval 0 to 2, we have looked up in the table and found that is 0.4772. So therefore, this is 0.5 minus 0.4772, and that's approximately equal, and that's equal to 0.0228. And that is the probability that you get your pizza in 20 minutes. It's really not very high. And what about the probability that you get your pizza in 22 minutes? We can do the same calculation. That equals probability that z is less than or equal to 22 minus 30 divided by 5, which is probability that z is less than or equal to -8/5, so -1.6. And that should equal to probability that z is greater than 1.6, and that should be 0.5 minus probability that z is between 0 and 0.6. That is 0.5 minus the probability that z is in the interval 0 to 1.6. We can look up this probability in the normal table. We just look for the z value that equals 1.6. We look for 1.6 here, 1.6 and 0. So that is 0.4452. So that is 0.4452. And the difference is 0.0548. So it's a little higher, but not much. So that is how you calculate normal probabilities. The last thing I want to mention is the sum of independent normal random variables. Let x and y be two independent normal random variables. So two independent random variables. They are independent, and x follows normal distribution with mean given by mu x, sigma x, and variance given by sigma x squared. And y follows also a normal distribution with mean given by mu y and variance given by sigma y squared. Then the claim is that x plus y follows also a normal distribution with mean given by mu x plus mu y, which is not surprising because expectation is linear. Expectation of sum of two random variables is the sum of the expectation of the two random variables. And the variance given by also the sum of the variances, because the two random variables are independent. They do not have correlation. Their covariance equals 0. Therefore, this variance of the sum equals the sum of the variances. So we're not going to go through the proof for this result. We just need to know this result, that adding two independent normal random variables will give us another normal random variable. Notice that this is not true. A similar conclusion is not true for other types of distributions, other distributions that are not normal. Similar results may not hold for other distributions. The book, section 6 of the book gives us an example where you add up two uniform random variables, two independent uniform random variables. You do not get another uniform random variable. So this property is kind of special for normal random variables. And that can be useful for our future calculations. And that's it for normal random variables.